Hello and welcome to Introduction to Machine Learning. In this module, we will look at advanced neural network concepts. So some of these will be going into the realm of deep learning, which is an advanced course, advanced subtopic within machine learning. So we will not cover a lot of these in depth, but it is good to get an introduction to these concepts when you are studying neural networks, because a lot of recent advances and research is focused on advanced neural networks. So the learning objectives of this module are that you should be able to write neural network loss functions that are for slightly more advanced ML problems, machine learning problems, than what you have been used to till now. You should be able to write some properties of natural signals for which special layer architectures of neural networks are useful, for example convolution and pooling. And you should be able to explain the reason for exploding and vanishing gradients in neural networks that propagate gradients to through many layers, and then see how long short-term memories can actually resolve some of those issues for recurrent neural networks, whereas certain other architectures such as residual networks can do that for convolutional neural networks. So let's start with slightly more complex problem than what you have been used to. Let's start with a multi-output regression problem. So here the setting is such that you have a target Ti, which is a continuous value, but it is not a scalar, it is a vector now. So for example, let's say you have T, I will try to draw it bold. So this is bold Ti, right? And basically this is a vector of several Ti1, Ti2, etc. So it has Ti1, Ti2, these are the scalars, and all the way up to Ti, let's say D, right, capital D. So this is the dimension of your target output. So what this an example of this could be that, let's say we are trying to predict the height and breadth of a particular object in an image. So image is the input, but height and breadth, both of these, or height and width, these are both continuous values. So one will form Ti1, the other will form Ti2 for the ith object or the ith image, right? And the neural network predicts y, and this y is also a vector, it's no longer a scalar. So this is also bold, and we have yi. Okay, so between yi and ti, what we want to do is we want to reduce the difference between yi and ti, and now it is not going to be a scalar difference alone. So we have yi also as a vector, which is yi1 all the way up to yid. Okay, so now the loss that we will use for this neural network, let's look at that, but first let's look at what the architecture will look like. So let's say we have inputs. So these are your input neurons. So this is xi1 all the way up to xi, I will use small d. Alright, and then you have some hidden layers. Okay, so this is fully connected. All inputs give feed into the next layer. Okay, and then we have yi. Okay, so yi1 and yi2. Okay, so this is yi1 and yi2. There are two outputs now, and each of these neurons in the hidden layer and the output layer have one bias each. So this is your yi1 and this is yi2 for the ith input. Okay, so now the loss function that we can use for this is based on L2 norm of the difference between Ti and yi. So we will take Ti minus yi, right? And we will take its L2 norm, okay, and we can square it, all right, and then we can take half of that, okay, and we can sum it over all I, and then we can divide it by n, which is the sum of which is the number of training points. I ranges from 1 to n. So this is going to be the equivalent of mean square error, but for vector output. All right. So if whenever we have multiple outputs to be predicted, then we can use a loss like this, which is a generalization. Now here we don't have a simple difference, we have a vector difference, and then we will take its L2 norm, and then we can square that. So basically it is going to be in some sense you can think of it as sum over I, sum over j, right? And then we have Tij minus Yij squared, okay? And this we will have a half here, and we will divide this by both n and d. Okay, so that is going to be the equivalent of mean square error in multi-dimensional regression output. So now let's take this idea of regression losses a little bit further. So if you remember the L2 losses or this mean square error, so this mean square error, if this is your error and this is your loss, the profile looks something like a parabola. Okay, that's your L2 loss. And the problem with this, or first the advantage of this is that whenever the error is small, the gradient is going to be small. The near the origin, the gradient of the loss is nearly zero from both the positive and the negative side. So for small errors, it's not going to make adjustments to the neural network. They are not going to contribute to the weight adjustments. But when your errors are either large positive or large negative, then there is going to be a large gradient that will adjust the weights of the neural network. So it will train faster to reduce errors that are larger in magnitude. So it may be desirable for many situations to do that, because here the assumption is that this works very well when your error is Gaussian distributed. But when your error is not Gaussian distributed, so your distribution of error, so this is your P of error and this is your error. So we are assuming that it is Gaussian distributed. So Gaussian distribution has certain properties that it is not considered a heavy-tailed distribution. A heavy-tailed distribution, an example of that would be something like when we have exponential distribution or two-sided exponential distribution, Laplace distribution. So in Laplace distribution, at some point it actually starts to exceed, right, because it is some constant e to the power some constant. So maybe error e and this e are different. So let's just write exp of minus c times mod of e, right? So this is your Laplace distribution, and then there is another constant k, so that these two so that it integrates to 1, or usually we use lambda and 1 by lambda. So here the idea is that for large values of error, no matter what these constants are, the tail is going to be higher than the tail of a Gaussian distribution, where we have e squared instead of mod of e, mod of error. We'll have error squared inside. So these heavy tail distribution basically mean that there are more outliers. There is more chance of an outlier compared to a Gaussian. So when you have more chance of an outlier, then to try to fit a regression output to that outlier is going to be problematic. So the output or the weights are going to be very swayed by the outliers. So an alternative to the L2 loss is the L1 loss. Okay, so here your loss is basically proportional to mod of E. Okay, and here what we see is that no matter what the error is, the gradient is always going to be constant in the positive side and always going to be constant in the negative side. So it does not get swayed by, it doesn't give undue importance to the outliers. It gives as much importance to an outlier as it gives to anything that is close to the origin. So that way it is a outlier rejection strategy, that is for which mean absolute error, MAE or L1 loss are used for regression. And that can also be used for multi-regression, where we can actually look at L1 losses in by taking the L1 norm of the t minus y, or the error. Now the undesirable property of this L1 loss is that near the origin it is still giving as much importance to small errors as it is giving to large errors, and by importance I mean the gradient, the magnitude of the gradient. So which is not desirable. So a compromise between L1 and L2 loss, so this is L2 loss, which is MSE, mean square error, and this is L1 loss, which is MAE. Compromise between the two is that there is a small region in which we use L2 loss. So this is, in this range we will use L2 loss, and outside of that we are going to use L1 loss with a smooth connection here. Okay, so you can easily work it out what the smooth connection is. So this size of the trough, we will call it delta. So this is, let's say, up to plus delta, and from minus delta. Okay, so within plus minus delta we are going to have a parabolic or an L2 loss. Outside of minus delta, less than minus delta, when the error is less than minus delta or greater than plus delta, we are going to have an L1 loss. So which means that once we enter this trough region, then the smaller, relatively smaller errors will have almost zero gradient, and those will actually not have any contribution in deciding the regression equation. The errors that are outside are going to have an increasingly more gradient, but after some time that gradient will become constant. After a certain error magnitude, that gradient will become constant. So I will leave it as an exercise to derive what this Huber loss, this L1 plus L2, it's not actually L1 plus L2, but it's like range wise, piecewise, either L1 or L2, which is called Huber loss. What is the expression for that, so that the L1 and the L2 terms, wherever they connect, they are both continuous and smooth.